Hi, welcome to lecture 27. In this lecture I'm talking about double-slit experiment, and I'll try to keep this fairly short because, surprisingly enough, there isn't actually very much new physics in this. It's really just another example of applying principles that we already understand. And the double-slit experiment is sort of famous because it's often quoted in, I guess, in the introduction to, say, quantum mechanics. But the context it's quoted in there is that the double-slit phenomenon that we see, the sort of pattern of light that we see, that the same pattern is also seen if you shoot, say, tiny particles through two slits. And that is usually one of the sort of hints that the classical mechanics doesn't quite seem to apply to very small things, and historically it was one of the hints that led to developments in quantum mechanics. But that does not concern us here, right? We are trying to figure out what is the experiment in the first place. We understand how is it an example of wave interference. The fact that that same kind of phenomenon is also observed with something we don't think naturally as a wave, that's a different story that you might study in a more advanced course if you're planning to keep doing physics. Alright, so here's what a double-slit experiment is. So here I wrote it out in green. It's essentially nothing but two-source interference, the way you know and love from the two speakers, for example, but with light. And then with the distance between the two sources, like the separation between the sources being a lot smaller than the distance where we analyze what happened. Right, so with the two speakers, we had a speaker here, and then the source here. Our point of interest here, we asked, is it constructive or destructive? Now we have two slits here and here. They're right next to each other, a fraction of a millimeter apart, and an even smaller fraction of a millimeter thick, and laser light falls onto it. Let's say it means we've got a coherent wave. Essentially a single frequency of light, and the waves just travel sideways like this. They hit those thin slits and then they spread out because of diffraction, right? A wave passing through a small opening is going to spread out on the other side. So that happens due to each slit. So each slit, the light will spread out. I wasn't able to draw this for the two slits, it's very close together. So it's almost like I have a source here and a source here. And they have to be very close because the wavelength of light is very, very small, right? It's the hundreds of nanometers. So having them be, a fraction of a millimeter apart is what we need in order to see anything, any kind of interference pattern. So essentially each slit acts as a source, and then the sort of geometric difference to the normal two-source setup is that the points where we observe whether it's a maximum or minimum, whether it's constructive or destructive interference, that is very far away compared to the separation of the two sources, right? So again, with the speakers, maybe the speakers were 2 meters apart, and we worried about a point that's 4 meters in front of one of the speakers. Now we have the two sources a fraction of a millimeter apart, and we worry about something that's, a couple of meters away, maybe a pattern on the wall in the lab. So the geometric difference means we can make certain approximations about where the constructive and destructive interference occurs, and the two sources aren't themselves producing the waves, but they are just 2 points from which light diffracts. But the interference calculation in a sense is the same, up to some approximations that we can make due to this extreme geometry of this distance here between those being a lot less than the distance to the screen. Right, but that is pretty much it. So that's kind of what I wrote here. Two slits are very narrow, very close together. Light diffracts, so each slit acts as a source. Let's analyze this situation. So here I've drawn two pictures. This is kind of the view from the top. Here I try to do a kind of 3D view. Hard to indicate any lengths or any quantities precisely, but it gives us kind of the picture of what's going on. As I mentioned, I look at this from above. So the two slits, they're next to each other here, and they're very, very close together. Right, so maybe this length L is a couple of meters, and this is a fraction of a millimeter. So remember to figure out, is this point here constructive or destructive? Like, is there constructive or destructive interference? So some chosen point, maybe on the distance screen here. I have to compare the distance from this point to the first source and the distance from this point to the second source. Right, those are the two lines that I draw. It's hard for me to draw here accurately because those two lines are so close together, right? You go from here to here, and then I go again from here to, well, a fraction of a millimeter next to it. And so there are really two lines here, and they're pretty much on top of each other, except one ends just a teensy fraction of a millimeter lower than the other. But it means the position of this I can fairly well give by just giving a single angle like this from the center line. Like that. And then imagine I pick some point here that's a distance y from the center. So just geometrically, what I can do here is I can say that y over L, like this length over this length here, is, well, technically it's a tan of this angle. Right? But because this angle is very, very small, if I look at the actual pattern, say of these sort of light dark fringes on a wall, this is what I observe, and you'll be looking at it in the lab as well. It's a few centimeters maybe, right, compared to a couple of meters. So the angle theta is going to be very small. So I can make this small angle approximation where I say tan theta is approximately theta. Right, let me write this down. Small angle approximation. Right, sine theta is approximately theta, and tan theta is also approximately theta. Obviously, sine is approximately tan. Right, geometrically, y over L is tan theta. Y over the blue length is sine theta. But of course, those two are pretty much the same length, given that this is just a few centimeters, whereas this is a few meters. Okay, so that's the sort of geometry of the setup as we sort of stand in the lab and look at it. Now let's zoom in on where the two slits are here. Right, that's this zoomed in view that I drew down here. Adjust my camera a bit. Right, this is my zoomed in view. I imagine those slits are a small distance d apart. And then I've got my two lines. Right? Those two lines are the two lines on top of each other here. They each point to the same point here. So those two lines, they meet on the far away screen. Right? This is like maybe a millimeter in diameter, like from here to here, like a millimeter, right? So they meet really, really far away compared to the separation of the holes. So those two angles here, they are, well, technically not exactly the same, but they're really darn close to being the same. And so I want to figure out, well, for this point here, that's some distance y above the center, right? How much longer is this path, or how much longer is this path? It's going to be a longer one, it's lower down here, right? How much longer is this one compared to this one? So this one starting at the top slit to here, versus this one the bottom slit to here. It's going to be a tiny difference, but also the wavelength of light is tiny, so maybe those are somewhat comparable. So here's how I do this. Well, let me first tell you how most accounts do it. Like, you read the textbook, you Google it, you find some explanation online. They make the following assumption. Say, pretend this line is parallel to this line, right? And then I draw a sort of line like this, and it's 90 degrees to both, and then I've got this right angled triangle. I mean, it works. It's, in my experience, many people find it confusing when they first meet it, because you're saying those two lines are parallel, but they also meet here. Two lines are parallel, they never meet. I mean, they meet at infinity, right? And mathematically, you might say, well, this is almost infinitely far away compared to their separation. And so it's technically a well-defined approximation. But here's how I would do it. I think that's how I would understand it. I think it's a lot simpler. Imagine I draw a triangle that is that this is one point here, and this is the second point here, like the upper, where the upper line meets the top slit, like this end here. Right, this is my other point. Then I want to make an isosceles triangle. Right, I want to make it such that this distance from here to here is the same as the distance from here to somewhere along the bottom slit. So it looks bottom, like the bottom path towards the slit. Right, so it looks something like this. Where my claim is not that those two are 90 degrees, that's another way to approach it. I'm just going to say those two are the same. I'm saying this angle here is the same as this angle here, right? So those 2 points, I picked this point such down here, such that those 2 points and this distant point on the screen, they form a really slender isosceles triangle. Like isosceles meaning 2 sides are the same in length. Well, if I look at this triangle, the angle up here that's too small to see is utterly, utterly, utterly tiny. Right? Utterly tiny. Those two angles are the same. Right, let's call this, let's not call it anything, right? Those two are, actually we call them alpha. They're both the same, right? By my assumption of how I drew this line, I could have drawn it lower down or further this way, but I picked the line that makes those two angles exactly the same. Then this is an isosceles triangle, so those two lines are the same. So that implies that this part down here, that is the extra length traveled from the bottom slit, like the extra length the wave travels, right, from bottom slit as compared to the top slit, right, by definition of this line. Now what is alpha? Well, because this angle here is utterly, utterly tiny, and though those two are the same, they are essentially both very much almost 90 degrees, right? So alpha is, I'm going to say approximately 90 degrees. I'm not making the assumption it's 90, I'm just, by them being parallel, those lines or something like that, I'm just saying, look, I picked an isosceles triangle and I can see one of those angles is utterly minute. In fact, it's about d over l-ish. Right? It's. I mean, really, I might write, maybe 89.996 degrees. Right, something like that. So it's really, 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 really close to 90. So that means this angle here on the other side, this one in here, is also really, really close to 90. Right, so this one here is essentially a right angle. I mean, this is essentially a right angle, so this is essentially a right angle. Right, so this one here, I'm going to write as if it were a right angle. So this is very much approximately, to an extremely good approximation, a right angle triangle. Right, and then we can look at this. The right angle is over here, right? So this is my right angle. So this is the hypotenuse, which is opposite the right angle. And so I guess the last piece I need to enter here in this diagram is that because these two lines are almost 90 degrees, and this line here, the horizontal one, is 90 degrees with the vertical one, this angle here is essentially theta 2. Again, to an extremely good approximation. And here's where I'm using this extreme geometry, right? All these approximations, this is almost 90, all those angles are pretty much identical to an extremely good approximation that all follows ultimately from this point being really far away. Which is why I was not able to apply this kind of analysis to the two speakers, for example. So the extra length right here is going to be d sine theta. So let's call, this is going to be my delta r, right? The extra, how much longer is one path than the other. And this is going to be d sine theta, but because the angles are small, this is approximately d times theta, right? Again, the small angle approximation. All right. So now we've got to put the pieces together to figure out, well, for what y values here do we get a maximum or a minimum? Right, so what do we have so far? We've got this here, and we've got this here. Right, so for what values of y, actually, well, yeah, you can ask that, is do we see constructive interference? Constructive or destructive, right? You might as well ask for both. Like, what is the condition? Right. So we're asking, where on the screen in the back do I see light? Where do I see dark? Light, dark. Like, what condition has to be true so I see a light patch here where the light from those two slits interferes constructively? Well, I know that the extra path has to be a whole number of wavelengths. Constructive, so if and only if, right? If the extra path traveled from one source compared to the other is a whole number of wavelengths, where n is 0, 1, 2, and so on. Of course, 0 would be right in the middle, where it's equal distance. Okay, now I know what delta R is. So I can write IE. It's constructive if and only if. Well, delta R is this thing up here. D theta, it's not d theta, some kind of derivative, is d times theta, right? Is equal to n lambda. So theta, the angle, has to be lambda over d times some integer. Could be 0, in which case it corresponds to just the point right here, right where the angle theta is 0. Of course, I can write theta as y over L, based on the geometry, sort of on the zoomed out picture. And so I have that y over L has to be equal to lambda over d times n. Right, that is my condition for it to be constructive. Or the way you often see it written is I'm going to ask for the nth bright fringe, as it's called. So the 0th is in the middle, and the 1st, the 2nd, the 3rd, well, the nth, right? The 10th, the 12th, the 102nd, right? And the nth bright fringe. So on my picture, start in the middle, like bright, dark, like the 0s, 1st, 2nd, 3rd, and so on, the same thing going in the other direction. Nth bright fringe is at y n. So I'm labeling the distance, the nth bright fringe from the center, by yn, and that's lambda L over d times n. Right, and you can think about what happens if I change my wavelength, if I make the wavelength longer, so I go more, have say red light instead of green light, or shorter, I put blue light instead of green light. You know, how will it change the pattern, for example? Or what if I make the distance between the slits wider or more narrow? Well, what happens then if I change this value, right? So you can think about what happens in those cases. Similarly, I can ask about the destructive ones. They, of course, occur when delta R is essentially n plus a half lambda, where n equals 0, 1, 2, and so on. Right? Because like a half, if the extra path is half a wavelength, like 0 plus a half times lambda, the two waves arrive out of sync. They arrive at opposite ends of the cycle, so it's going to be destructive. If it's 1.5, like 1 plus a half wavelengths, again, they're going to arrive out of sync, so the interference is destructive, and so on. So I can do exactly the same range calculation I did here. Maybe you can fill in the details, but it's literally the same as this, except the n is an n plus a half. And I'll get that the nth dark fringe is at, I guess, could I call it yn2? Right, let me label it maybe the mth dark fringe, right? Let me just label those with the letter m rather than n. Ym is equal to lambda L over D times m. I guess I'm going to put plus 1, where the first fringe is m equals 0. That's confusing, isn't it? The zeroth fringe, dark fringe, is the first one left and right of the middle. Usually you might count differently, and then you'd put a minus in here, right? So this is a matter of how do we count. I'm going to actually change it to this. Bit of an afterthought here, and I start at 1 because then there is no like zeroth dark fringe, because the middle is bright. So as soon as I go to left, I say this is my first, right? Let's leave it like this, so it can be less confusing when you compare this to what you might find, say, in the lab or in other sources. Either way, right? It's physically clear where those light and dark fringes are. Those are the conditions. It's just, so let me re-emphasize this. It is just a matter of calculating what is the difference in the path length from each source to the point. Just the same as you did, say, with the interference of sound using two speakers. What we can do, because this distance is so much further than the distance between the sources, the separation of the sources, and because this angle is small, like we're looking kind of almost straight ahead, a little bit to the left, a little bit to the right. Because those angles are small, that is why we can make these approximations here and here, and we get this sort of simple result that just labels where the bright and dark fringes are in a way we weren't able to do with the two-speaker setup. So don't ever apply this equation to the two speakers. I've seen it enough happen in exams. Don't do it. It's wrong, right? It's wrong unless the two speakers are really close together compared to the point you are asking about whether it's constructive or destructive. All right. So enough of that. Let's do a little variation on it. Another variation of this I'm not going to go through in detail is what's called the diffraction grading. I actually prepared a little picture for this because I don't trust myself drawing this. So diffraction grading is like a bunch of double slits. You just put slits at equal intervals into some kind of mask, what you should call it. Some kind of, a card or some film that you cut little slits in. And now imagine light arrives, right, and then it diffracts as you go through each one. So it's kind of a multi-source interference, not two sources, but a lot of sources, and maybe 1,000 of them. And then they meet at some faraway point. So all those lines, right, they all meet at some distant point, say on a screen. I can do exactly the same thing geometrically that I did with the two slits. Like those two I treat as two slits. Now if this distance here is one wavelength, which means constructive interference, then just by geometry this distance is two wavelengths. So again, constructive 3 wavelengths, 4 wavelengths, and so on. So that'll lead to constructive interference. If this were half a wavelength, then like extra path for this one here, then this would be 1 wavelength. So this and this one, they would be destructive. Then this one would be constructive with this one, but the next one would be 1.5 wavelengths extra, be again destructive. So in the end, they all cancel out. Like each one cancels its neighbor, as it were. If this distance here is half a wavelength, or 1.5 wavelengths, right? It doesn't matter. So the effect is that you get the same thing as with a double slit, except a lot more light falls through it, so it's brighter. Now, one nice use for this is that I can shine white light on it, and the diffraction grading will split it into different colors, because different colors of light have different wavelengths, and so they're going to have constructive and destructive interference at different points, right? So that's why I wrote down here it's useful, e.g., to split white light into different colors. So one application of this is, imagine you look at the spectrum of some element, some chemical element, like you're trying to figure out what it is, and each element has a certain spectrum, like it emits light at a particular set of wavelengths based on, you know, the atomic processes inside. Then the light created is going to be some sort of mix of colors, but then I can send it to diffraction grading, and the different colors will go in different areas. Like the red might go up here, the green might go there, the purple might go here, and the ultraviolet somewhere else. Right, so you can use this to sort of split up mixed light into the individual colors, for example. But physically, geometrically, it's just a glorified double slit setup. All right, thanks for watching.